Okay, welcome to AutoJoint System 3, surface sampling. In this video, we've taken the AutoJoint 2 intersect system, and we've just kind of have that here, and then we created some new objects, just two objects to begin with in order to do some easy testing. And what we're going to do is we're actually going to birth extra surface sample particles on top of these particles, and have those surface samples look around for other surface samples, figure out if it can find some surface samples who are from a different particle, and then when it does that, we're going to set up some limiters, and then we're going to go ahead and filter out all of those valid ones that have found other partners, and then we will go ahead and create the joint based on that. So we'll go ahead and do a little maintenance here first. We're going to go ahead and create a new dynamic set. We'll stick this auto joint system in there, and we will actually go ahead and, if I can relocate that guy, I'm going to go ahead and disable it to begin with, and we'll call this dynamic set auto joint 3. Let's actually put a little descriptive name in there so that we can easily recognize what this thing does. Surface sampling. Maybe we hit the limit. Surface samples. That's great. Okay, so we'll create a new dynamic set, and this is kind of where you have to make a choice about how you structure your black boxes in your systems. Really, what we want to do is we want to take these object particles at birth, and we want to create some surface particles on them. For that, we're going to go ahead and need a new particle group. We'll just call that joint surf samples. Yeah, that'll be fine. And then what we'll do is we're actually going to build this right into the creation phase here. We'll go ahead and create a position, a surface position helper. And we're going to take the particle shape of this object particle. We're going to go ahead and then create a position born, and we will create some joint surface samples. Pistol shot, let's go ahead and just create whatever for now. Their lifespan we're going to set to 0 because we only want them to exist when these particles are born, and only for that first evaluation of the tree. We're actually going to set up and create these joints all in one sample. Okay, we want to sample face information, no UV specific stuff, and we'll just randomize that seed. The position will feed into this. Each one of these object particles is going to create these, so we connect the particle. And no speed, because we don't want any displacement. Our joint surface samples, we need to modify these. Let's make them dots, not renderable, and let's make them kind of a blue color. Okay, so we get a bunch of particles there. Let's actually go one little further step. Let's take the particle data of these object particles, access their size, and then we'll use that size as a multiplier to control how many surface samples are created. Like we've mentioned in some other videos, though, size is not really the best measure of a particle's either total surface area or volume. Surface area or volume would be much better. What you can do is you can actually write a Mac script that will measure that and store that as a user-defined property on that source node. And then what you do is you take a look at our user-defined props tutorial script operator, and you can access that birth node, and you can modify this script to read whatever user-defined properties you want, and then output those values either directly into an operator or into a memory operator so that you can use that later. Okay, so let's take a look. As we increase this multiplier for size, you can see that it changes the number of samples. That's fine. Let's go ahead and collapse some of these down. And one of the other things that we want to do is we need each one of these surface samples to remember who created it, who is my parent particle. Reference is one way to do that, although we ran into a bug where reference was not being read properly from a p-search, so we find that memory tends to be a little more reliable, I guess. And one of the things with memory in systems like this is we usually want to create kind of our key memory variable holders outside of the outside of the dynamic sets. We want to create them kind of at the top level, so that as we're dealing with dynamic sets and cutting and pasting things, anytime you cut a dynamic set, if you were to select this and say cut, if this dynamic set contained any memory variables, it would break all the connections out of every other dynamic set, which is a big bummer. So we like to create a memory operator at the top of the system and store all the variables in it. And so this one we're going to call it my parent. And let's go ahead and rename this memory so that we actually know, hey, this one's got the variables. We'll just call this mem auto joint 3. Okay, so that'll sit here. You can see it clearly in the memory list. It contains that variable. Now when we go into the born dynamic set, let's access this memory here, create an input, and these particles, the surface sample particles, need to know who created them. So we'll take that object particle and store that in their my parent variable. Kind of do a little cleanliness organizing there. Okay, so that's pretty much all we need for that. Then what we do is we're going to need each of these surface samples to search around and look for other surface samples and say, hey, do you have a different parent than I do? And if they do, then we want to go ahead and either mark them or put them in a new group, because those new pairs are going to be the ones that where we actually want to think about creating joints. So we'll go ahead and do this. Surf sample search. And we will tell the, I think we have some logic in here. Go ahead and copy that. We're going to tell the joint surface samples to search and search for the group, which is the same as this group, same as themselves. And let's take a look at our distance that we want to search for. You have to think about valid distances and how far things should really search, where you really want joints to be created. In this case, if you take a look at this scene, if there was another object on this side, this right side, we would not probably want this particle to create a joint over here on the right. We would want this particle to create a joint to this guy, and then this guy to create a joint to this guy. That way you don't get any kind of funky joints through other objects. So we have to kind of limit that by distance. So we'll just do a little measurement here. It looks like we're using the line tool, and then down here in the bottom it shows us that distance that we've got. So about 10 units should be fine. So let's stick that in there. Okay, and then what we want to do is we actually want to ask both of those particles. We want to ask the main particle who is doing the searching, as well as the found PIDs. We want to access their myParent variable. So we'll just add that, duplicate it. Oops, screwed that up. Let's expose that. And what we want to do is we want to do a little comparison of these PIDs and see if they are the same or not. And if they are not the same, then we want a true value. We actually have a M3D condition called is not equal, and that just takes two scalars and compares them. And if they are equal, then we output a 0. So if they're not equal, we output a true. So okay, so if they're not equal, and we also want to do another little limiter here. We want to limit the number of possible connections going back and forth. So we're actually going to test if this particle doing the searching is less than the PIDs that it finds. It's kind of a fast, easy way to limit those number of connections. Otherwise, you start to get two valid entries per search, which can be a little much. So to do that, again, M3D condition, we've got less than. So we'll test this PID against all of these found PIDs. And remember, these are iterative, so for each found PID that it finds, it's going to go ahead and do this whole calculation with all these. So if these two conditions are true, Then what we'll go ahead and do is we'll move the particle into a new group. And sometimes I recommend that you don't use too many new groups. You just put a little memory tag on these. But for this particular case, it's kind of handy to be able to visualize it. So we'll call this joint surface keep, because these are the locations where we actually do want to think about creating joints. So we'll go ahead and we will say if this particle finds some other particles and these it's got a different parent and this searching particle is less than the found PID, then we can go ahead and move this searching particle into this specific group, which will be the joint surface keep. And so let's go ahead and see what we have. We'll update that, and now you can see these purple particles down in here. And so these are all particles who found, and you can actually see that they found, they're all on this one specific object since it was the first object created and all of its children particles. That'll be fine. And so all these surface particles found other surface particles, and they had different parents, obviously because they're near that other edge. Nothing else out here found. So let's go ahead then and create our next rule, which is going to ask all joint surface keep. We want them to do a p-search also. And p-search can be a little expensive, so we try not to use too many of them. I know this isn't really the best example, but we're going to need to do a p-search here that is going to limit how many of these are going to be able to create joints. But part of the problem that we haven't really gotten into, but it does exist, is that all of these joint surf keep particles, they need to know these two particles, these two orange particles. They need to know who they are so that later on we can actually create that joint. That's kind of a step that we skipped over a little bit. Sorry about that. Let's jump back into our surface sampling. And what we're going to do is we will go ahead and create a new memory because we want to store some information for this particle. We want this particle who successfully found other surface samples. And we're going to want to control this on, so we'll expose that. We want, we're going to actually need two new variables. And so when we click these on this, we're going to click on the memory auto joint so that it actually creates those variables on this particular memory operator. We're going to create a particle called joint2 and another one called joint from. And then what we'll do is we will go ahead and take this searching particle who found the other one. We'll take its parent particle, this orange particle, and store that in the joint, oops, not the joint 2, but the joint from. And then we'll take the surface particle who had found and access its parent, because we want to create a joint from this particular particle, this orange particle, to this orange particle. So we'll put that in the joint 2 there. And we only want to store this memory value when these conditions are true. Okay, now this is all fine for a simple system, but actually what will happen is on a large system with a lot of objects, we're going to need also a way for these joint keep particles to know what the two particles are that it's jointing. This joint 2 and joint from, those are fine. We can use those to create the joints, but we're actually going to create a new variable here, an integer, and this is we'll call this joint pair. And this is a little bit we're kind of looking forward. We've done this before, and sorry for not walking all the way through it. It can be a little better discovery to actually go through the whole process. But we want these joint keep particles to store an integer that contains its joint from and its joint to. We had to create a script operator to do that. It's a pretty simple one. Let's see if we can actually find it. It's called Combine Unique ID, and this will be under our assets under, I think, M3D script operators. And what we do here is we take these two PIDs, the parents, and we go ahead and we're going to store that in the joint pair. Let's go ahead and take a look and see what we get there, because that can be pretty useful. We'll turn on, expose that to debug, step forward a frame, step back. Okay, so you can see that actually what is happening here is it's showing us 17 and 41. And chances are that's probably particle ID 17 and 41. Let's go ahead and show those. Oh, well, it's actually 174 and 1. That's okay too. These, it's not the most scientific method, but it is a way that all of these marker particles can then know, hey, we're all keeping track of these two source objects. And the reason this is going to come into play is because when we end up limiting these number of joint keep particles, when we do this search here, we need to go ahead and ask them, hey, do I have both the same joint to, joint from, or in our case we can just test the joint pair. So if you did not want to use the combined ID, you could actually test the joint to, joint from. We'll just go ahead and test the joint pair of these. And what we'll do again is just steal the, in this case, actually what we want is the, we want to know if they are equal, because we only want to reduce the joint keeps who are the same. We want to kind of boil these down and remove a whole bunch of them. We have too many of them in one location right now. We don't want to create joints at every one of these. We actually want to reduce this down and have some control so that we can control how many joints are created there. To do that, we will go ahead and we'll say ask these particles if they have the same joint pair integer. So if I can actually, let's see, is equal. Okay, so if they are equal, then, well, let's see. Right, if they are equal, we're going to go ahead and end up killing one of them. But now we have to watch out, because we'll kill the found PIDs. We're actually probably going to also want to test if any one of these is less than the other. Otherwise we run into the chance that it deletes them all. But looks like we're okay so far. This is probably because our searching radius is not very large. It's only set to 10. If we increase this, okay, well there we get, looks like we still have two of them located together. Let's go ahead and put in that less than, just as a test. If this particle is less than this particular one, and both of those are true, then we'll go ahead and kill the ones that I found. Let's check our p-search, make it nice and big. Okay, so with a large enough value on the p-search now, we're able to limit this. Let's go ahead and tell our joint surface keeps to display as ticks. A little easier to see. You can see that we only get one valid location now. And if we adjust this p-search radius, we'll actually be able to reduce that, and we can actually control how many joints can be allowed to be created there. So if we increase this a little bit more, we can get 3 joints that will be valid. And remember, all these joint surface keep particles, they actually, remember, they get stored and they get put in this group when they used to be surface samples, but they also end up now having the particle who they're jointing from and who they're jointing to. And let's go ahead and call this particular rule that we just made, let's call this filter out joint surface keep. And then finally, we'll go ahead and set up the jointing. Let's turn off debug. We'll call this auto joint 3. And this is going to be a little bit different. We're going to end up ripping out a whole lot of this. We don't need the particle age. Remember, all these only have a lifespan of 0, so it's all during the first evaluation. We don't need this intersect marker anymore. Let's go ahead and remove that. Nor do we need the intersect. Let's get rid of that. We'll keep that joint counter in here just for now. The p-search, we don't need that anymore, because what we're going to do is we're going to have these joint markers who are still alive. Joint marker. We're going to have them go ahead and access their memory and take the joint from and the joint to, and we will go ahead in this case we can actually test, hey, the joint from, the joint to, count how many joints they already have, and if it's currently 0, we'll set that to 0. If the number of joints existing between them is already 0, then we can go ahead and turn on the joint. We can set, we don't want a joint from the, sorry, this is not the joint marker we want to be dealing with the joint surface keep, because it actually has the memory value of the joint from, joint to. It's these purple particles. Sorry about that. So we're going to take the joint from, create a joint there, to the joint to particle, and the world position, in this case we'll go ahead and just use our joint keep particle position. Okay, and then we've got the joint marker being created. Let's go ahead and see what we get there. Okay, well, it looks like a little issue actually. Joint particles, let's go ahead and see. Oh, well, yeah, that explains it. I mean, we set up this limiter here to control how many joints were created, and our joint marker is actually this PID here, 304. Let's go ahead and change that color just so it's not quite the same there. There we go. So if we increase this number to, that allows or tests how many joints already exist between those two particles, if we increase that threshold to allow more particles, we can actually enable that. We actually don't really need that in this case, because that kind of limiting we actually already do in the filter out. You remember, by our p-search values, if we decrease this, we're going to allow more pairs to be created, and so we can actually allow more joints to be created. In our case, we'll go ahead and kind of control that, increase that, not too many joints in between them. Okay, let's go ahead and just hit play, and you can see that our object is jointed. Okay, and so now here's the beauty of this system, is that once we've got it built, we can go ahead and take a look at our other layers. We've got a few more objects in here, and we'll go ahead and tell our objects to pick all of those, or at least the 3 that it did not have already. Turn on changes affect all to affect all these objects. Double click instance shape to set that, and then we'll go ahead and hide that layer and show TP now. You can see that, of course, we get our new objects here, and actually, are they all going into the no, some of them were not. We did not update the group that they go into, so they all go into the objects group. You can tell some of them were white. Now they're all orange. Okay, and you can see all those joints being created in between them. And then when we go ahead and hit play now, well, that's what we get. Let's actually give ourselves a little more falling room. Exciting. Yeah, not a lot happening there, but we'll just double check our settings. Collision environment, voxel grids 1, so it's face accurate. Objects also, voxel grid 1. Our samples, 96 samples a second. And remember, we are on film time, so 24 FPS. Joints usually behave much more stable, are much more stable when there are more samples per second. That gives them kind of a finer time sampling to evaluate and kind of maintain their stability. If you start to get joints that get all wacky and bouncing around too much, try increasing your samples per second. Also try modifying the joint data and allowing them to be breakable can be helpful. Okay, let's do a little cleanup here. We don't need that stuff. Double click these to clean. Okay, so just to review, one last little run through. We bring our objects in with object to particle. We take a look at their size, use that as a multiplier, get their particle shape with a surface position, and then we create a bunch of joint surface samples all over the surface of each of these particles, these object particles. And we have to have those surface samples remember who they came from. Then we get into the sample searching. These surface samples, the blue particles, look around, find other surface samples, and if they're from different parents, and if the surface sample is less than the other surface sample it found, its PID number, then we can go ahead and we can put that sample doing the searching into the joint surface keep, which is those purple particles. So it's going to keep all those locations as potential joint locations. But we also need to store the two parent particles. We need to know, well, if it does find a surface sample from a different parent, make sure we keep track of those two parents, put that on the joint surface keep particle, put that information on that particle, so that after we filter these out, we want to reduce the number of joint keep particles, joint surface keep. We want to reduce that in order to control the number of joints. And then when it comes time to actually create the joints, the particle who's doing it is that joint surface keep particle. And it just looks up in memory, says, hey, I'm jointing from this particular parent to this other parent, and create that joint. And remember, the limiting for checking the number of joints really also already happens here in the filter out, because we can control with this p-search radius how aggressively or how far each of these joint keep particles searches for other joint keeps. Okay, so we had let's see if we can actually test. I'm going to see the number is 79 there, so let's actually reduce our or increase our limiting there. So our joint surface keep particles, we have 79 of those. And this is kind of the funny thing about TP, is that particles don't really die on the frame that you might think they do. You see here with this joint surface keep, we look and see if it has the same joint pair integer, and if it does, and if this particle is less than this particle, then we kill this found particle with the particle die. However, this particle is not really dead through the rest of all these dynamic sets until it gets to the bottom, and then the sampling starts over. That particle is still kind of kept in memory. So one of the things that we may have to do is use a condition called, in our tutorial script operator, called isAlive, where we can actually test, hey, is this joint surface particle really alive? And if it is, then go ahead and access its memory and create all this. Or we could expose this, the on the SC joint, and use that. Okay, well, we'll go ahead and save this out. I know that we had a few little bumps in that video, but I think you probably get the picture. You can certainly dissect this, and we can talk about it on the forum if need be. So we'll go ahead and save this out as end, and we'll go ahead and move on.